The learning objectives for today. Yeah, you need to solve the chemical engineering problems associated with the chemical reactions involved in a gas mixture. Define and apply the extent of the reaction concept. So where the reaction is going, where the rate is going. Apply the general criterion for equilibrium to chemical reactions and derive the expression for a chemical potential of a component in the ideal gas mixture. So that's by the end of it. It's not as useful for second year. It's very, very, very useful for third year for everything. Define the temperature dependence of equilibrium constant. That's quite useful. And apply the Le Chatelier's principle to a reaction mixture at equilibrium and calculate the equilibrium composition of an ideal gas. This is from high school chemistry, quite important as well. And differentiate between the equilibrium constant and the Kp formulation of the equilibrium constant. Again, fairly important. There are a number of competing factors for selecting reactor operating conditions. First one is the rate of the reaction, and the second one is the equilibrium conversion. So you can have equilibrium conversion, but it might take years to do. So it's not going to be economical. So it needs to balance the equilibrium conversion, and the rate of the reaction should balance. And that all balances with respect to the size of your reactor. This is not part of this topic, but in general, it applies to the size of your reactor, how much your reactor will cost to build, the material you'll use, the catalyst you'll use. Rate of reaction and equilibrium conversion depends on the temperature, pressure, initial composition, and also reaction also depends on the catalyst. Now, you have to choose your catalyst based on the various parameters to make sure your reaction rate is high enough, but also the byproducts and the free radicals, whatever is part of your reaction, does not exceed the requirements. Equilibrium conversion does not depend on the catalyst. So the actual conversion has nothing to do with the catalyst. Catalyst only relates to the rate of the reaction. Experimental studies are needed to determine the reaction kinetics. So these are all based on experimental studies. You can't really theorize them. And thermodynamics can say nothing about the reaction rate. It only tells you whether the reaction takes place or not. So, if you're wondering why this is part of this topic, welcome to the club. It is only concerned with the final equilibrium conversion, irrespective of how long it takes the system to reach the final equilibrium state. It may take seconds or it may take years. So the equilibrium conversion only relates to whether that reaction takes place. The rate is based on your other parameters: temperature, pressure, initial composition, and catalyst. Equilibrium conversion dictates the overall likely profitability of a selected route, while kinetics determines the size and the likely capital cost of the reactor. Now, they are quite related if you're a chemical engineer. Not so much if you're a chemist, but very much related if you're a chemical engineer, because the profitability is based on your capital expenditure and operating costs. So it's a balance between the conversion and also the kinetics. For example, looking at the Haber process for ammonia production. It's highly exothermic reaction, so you need maximum conversion. You get maximum conversion at low temperature. But to minimize the reactor size and cost, a higher rate of reaction is required. So you need higher temperature. So best reaction at low temperature, small size at high temperature. So how do you balance that? To minimize the reactor size, you need a high temperature. So we define its most profitable. So imagine a profitability triangle. So you're trying to be in the middle. The amount of money you'll make, the amount of expenditure, and the quality of the product. That's the conversion rate. To partially offset a drop in the equilibrium conversion, both a high pressure and excess of the one reactant is used. The reactor conditions need to be carefully chosen in order to optimize both capital and operating costs. Why do you think a high pressure is used? Do you guys remember the Haber process for converting ammonia? Do you want to look it up? So, you have N2 plus 3H, 2 turns into NH3, 2NH3. So why do you think a higher pressure will gain a higher conversion rate? You can see that, right? This is from high school chemistry, and also quite important. That's pretty much it. So your equilibrium is shifted, so you have a higher number of products. Le Chatelier's principle. And why an excess amount of reactants does improve your reaction rate? So if higher pressure moves your equilibrium, what does the excess amount of products do? Sorry, excess amount of reactants do?
The system moves to readjust the equilibrium by forming another.
Exactly. So it's pretty much the same thing. That's why. So what you do is, based on experiments and reaction rates and conversion rates, all of them are experimental. You can calculate what is the most efficient route to ensure your reaction is profitable based on the size of the reactor. So you have to take all of this into consideration when you're designing a reactor. But it's quite well proven, it's all experimental. So you do 10, 15, 20 years of R&D, and from there everyone else can copy your reactor within 6 months. So if you're wondering why drugs are so expensive. Not those drugs. Usefulness of second law of thermodynamics. Without the second law, it would not be possible to determine the equilibrium composition. It has some uses. Without the second law, it would not be possible to find a related property called the extent of a reaction. So how far the reaction has gone so far. Your residence time. The equilibrium relation derived using the second law also provides a theoretical explanation of the experimental observation made by Le Chatelier. So basically what we just discussed was Le Chatelier's principle. The experimental observation by Le Chatelier became famous and is known as the Le Chatelier's principle. So general reversible reactions. Let's say V1A1 plus V2A2 is converted to V3A3 plus V4A4. V1, and in standard chemistry books, that's usually lowercase a, higher case a, plus B plus C plus D for your reactants. Now, these can be replaced by any kind of reactor. And we'll see it as we go through it. Where in the upper equation, Vi are the stoichiometric coefficient of a reactor, reactant and product species, so number of moles being converted, and Ai are the various chemical species taking part in the reaction. So for ammonia, this is 1, this is 3, this is 2. These are your Vi Vj and Vk, I think. Usually. You can call it anything like the sign conversion for a stoichiometric coefficient is as follows: negative for reactant species and positive for product species, 0 for inert species. So when you're doing an energy balance, you're doing any kind of reaction balance, it's always negative on the reactant side and positive on the product side. It's good. Stoichiometric coefficients have no units. Number of reactant, there are the number of molecules that are consumed and the number of product molecules that are produced. Again, remember the Haber process. In relation to the first equation in stoichiometric coefficient, if delta N1 is the amount of reactant species 1 that reacts, then delta N1 is V2 over multiplied by V2 over E1 must be the amount of reactant species 2 that reacts with it, and V3 over V1 is the amount of products species 3, and V4, that should say only 4, not 34, over V1 is the amount of product species 4 formed by the reaction. So going back to ammonia synthesis, the Haber process. Initially, the amount of reactants N2 at initial stage is N0, so it's not 0, it's just the change. So at initial it's the 0 stage, 0 residence time. Reactants, when it's reacted, it's delta N N2, delta N H2, and delta N NH3, and the reaction balance is delta N N2 plus delta N N2 over V N2 multiplied by VH2, and the delta N N2 over V N2 multiplied by VH3. Now that's just an algebraic balance of that equation. It is a slightly easier way of doing it, but for purposes of this lecture, this is how it's taught. Notice that the reactants and products are consumed. We'll do a slightly better version tomorrow. Notice that the reactants and products are consumed and produced in fixed ratios. So the amounts you consume needs to be a ratio of the amounts produced, and it all balances to 1, which depends only on the ratio of the respective stoichiometric coefficients. Also, the delta NH2 equals delta N N2 over V N2 VH2. Therefore, the delta N2 N of N2 over V N2 equals the delta N H2 over VH2. So it always sums to 1. It's a stoichiometric balance. And the same applies to delta N H3. So all the reactant amounts have been expressed in terms of delta N N2. So the amount of N2 being converted. The quantity is the same for all reactants and product species. So delta N N2 over Vn2 equals delta N H2 over VH2 equals delta N NH3 over VNH3. So remember, V is your stoichiometric coefficient. So that all balances out. This is true for all reactions. So delta N, again, delta N1 over V1, 2, 3, 4 equals epsilon. And each of these coefficients are the same and are all positive. So you can actually define a reaction based on epsilon. Where epsilon is the extent of a reaction, it's also called the degree of a reaction or the progress of a reaction. And for a batch system, the extent of a reaction has units of mole. And the extent of a reaction is usually positive if only reactants are present initially. And it may be negative if only products are present initially. So moles of reaction. 2A plus 3B times into 4C. So a stoichiometric coefficient are normally integers and are small as possible. A situation where epsilon 1 equals 1 mole would mean 2 moles of A would have reacted with 3 moles of B to produce 4 moles of C. So to produce 1 mole of C divided. If the reaction equation had been written as follows, 4A plus 6B turns into 8C, then a situation where epsilon 2 equals 1 mole would mean 4 mole of A would react with 6 mole of B to produce 8 mole of C. But if both reaction equations are the same, so both are exact same conversions, then the equation describes the same system. Epsilon 2 would equal half epsilon 1. For any species I in the reaction mixture, the change in amount of I is delta Ni, and it's given by delta Ni equals Vi epsilon. So remember what epsilon was, it's delta N over V, delta Ni over Vi. Since for a specific species, since delta Ni equals Ni minus Ni initial, so the amount reacted, then Ni equals Ni initial plus Vi epsilon. And these equations apply to each species. This is a way of balancing that whole equation, defining everything algebraically when you're, let's say, writing a program or trying to calculate it all in one go. Where Ni0 is the amount of I, the species, before the reaction, and Ni is the amount of I when the extent of a reaction is epsilon, so how far the reaction has gone. And Vi epsilon is the amount of I that has reacted, so the amount of that species, let's say N2, that has reacted, either consumed or produced. So the amount that was converted, let's say, to ammonia for N2. The amount of reactant will be negative for a reactant species and positive for product species. Negative reactant, positive products. Sum this expression over all species. If you sum these expressions over all the species, N equals N0 plus V epsilon, the sigma means that's the sum of all species present in the reaction system, either before the reaction or later when the reaction is taking place at that specific reaction progression. Right? So N equals Ni, this sigma of Ni, the summation of all the species. And N0 is the sum of Ni0, moles of species present initially. So the number of moles initially, number of moles after reaction. And V equals the sigma of Vi, overall stoichiometric coefficient. So Vi, Vj, Vk, the sum of. So in ammonia, reaction takes N2 to be species 1, H2 to be species 2, and NH3 to be species 3. So describing ammonia in the same terms, N1 initially N1 0, N2 0, N3 0, and the summation is N0. When reacted is V1 epsilon, V2 epsilon, V3 epsilon, and V epsilon is the sum, and the remaining is N1 equals N1 0 initial plus V1 epsilon, so how far the reaction is taking place based, and it's related to time. N2 equals N2 0 plus V2 epsilon, N3 plus V3 epsilon, and the total, the sigma is the number of moles total. So Ni equals Ni0 plus Vi epsilon. Reading horizontally across each table sums over all species. The sigma 3, so for the 3 species, I equals 1, Ni0 equals N0, For the three species Vi, epsilon equals V epsilon, and for the three species Ni equals N. So the total number of moles. And the extent of reaction is the same for each species and the same overall. So because it's the same reaction, how far the reaction takes place is interdependent on each species. So the amount, because there's no inerts, there are no partial conversions, just one reaction. So everything will sum to 1. Dividing the moles of each species by the total moles present, composition of, so this is the composition of each species in the reaction mixture. Xi equals Ni over N equals Ni0 plus Vi epsilon over V0 plus V epsilon. And ammonia reaction, they're all dependent on epsilon. So initially, V1 epsilon, V2 epsilon, V3 epsilon, and you've seen the balance, equation balance of the composition. X1 equals N1 0 plus V1 epsilon over N0 plus V epsilon. And for X2, it's N2 0 plus V2 epsilon, the extent of the reaction, over the N2 plus V epsilon, and X3 equals N3 0 plus V3 epsilon over N0 plus V epsilon. So the Xi, the total composition, needs to equal to 1. And that's how you check it, by balance that. As the reaction proceeds and the extent of the reaction changes, the composition always sums to 1. As the extent of the reaction changes, the amount of each species and the mixture composition change. And to find the final equilibrium extent of a reaction and the final equilibrium composition of the mixture, the extent of the reaction lies between 0 and the moles of limiting reactant initially present divided by the stoichiometric coefficient. So there's usually a limiting reaction, and that's usually the slowest reaction. Actually, it's always the slowest reaction. And this condition arises because if species I is the limiting reactant, then Ni0 is larger or equal to Vi epsilon. Hence, it follows that epsilon is smaller or equal to Ni over Vi. So if your initial reactant always has to be larger, or there's not going to be any movement or in equal. But in equal is an ideal situation. So remember, you add excess N2 and 3H2 to move the reaction. It's the same concept, or it needs to be the exact same amount, but then you have to have a thermodynamic drive. Gibbs free energy. The key requirement to find the property of a system which is fundamentally dependent only on the intensive properties of a system, which are as follows: temperature of a system, pressure of a system, and the composition of a system. So Gibbs free energy is the required property. In topic 5, we went through dg, the change in Gibbs free energy to satisfy dg, to change in Gibbs free energy smaller or equal to VdP minus SdT. Hence the extent of a mixture. This will be extended to mixtures later. That later refers to next year. The equality applies to reversible changes and inequality to irreversible changes. So you've seen this in the last topic. Hopefully you remember some of it. For a reaction system where temperature and pressure are fixed and uniform throughout the system, the Gibbs free energy shows how a system will move towards a state of equilibrium. So dg with respect to temperature and pressure is smaller or equal to 0. This determines where your equilibrium is going to move. So it refers to all chemical reactions as well. It refers to thermodynamic behavior, so pressure, temperature, volume changes, but also to chemical reaction changes. So if it's you need to minimize this to find the equilibrium point of your reaction. That's all you need to know for now. Whenever a system is far from equilibrium, it changes irreversibly, and compositions are so the compositions are changing. It's a real world situation. In this situation, inequality applies, and the reaction must proceed in the direction of decreasing Gibbs free energy, so to reach equilibrium. That's why you add more and more of your reactants. You increase pressure to make sure you don't reach or don't minimize Gibbs free energy. And you can actually calculate what's the most optimum stage of your reaction thermodynamically as well. Then you do it experimentally to check it out, because sometimes it doesn't follow. When a system is very close to equilibrium, tiny changes occur reversibly. So let's say you're at equilibrium for the Haber process, you're converting N2 plus 3H2 to NH3, but you're also converting it slightly back, even though it's thermodynamically very difficult, because it doesn't fully convert. It's kind of in a transition state. Just a chemistry note, to be honest. In this situation, the equality applies. So dG Tp equals, with respect to temperature and pressure, equals 0. Note this is a general condition for both phase and chemical reaction once the composition is included. So the point of chemical equilibrium occurs at the minimum total Gibbs free energy. So this is how you can determine equilibrium, or this is how you can calculate Gibbs free energy by experimentally finding the equilibrium point. And from there you can model a reaction. No, doesn't really work that way. Equilibrium may be approached from either side. It's far from equilibrium, then the total Gibbs free energy must decrease, and the point of equilibrium occurs when total Gibbs free energy is minimized. And epsilon refers to the extent of your reaction. So there is a point where your reaction progresses so far that it reaches minimum Gibbs free energy, so it can't go any further. That's why you have a limiting factor. So close to equilibrium, tiny changes in total Gibbs free energy are 0, in theory. The strategy now must be to drive an expression for the total Gibbs free energy of a reaction mixture. Fun stuff. Then it should be possible to drive an expression for chemical equilibrium, after which it should be possible to calculate both epsilon of the equilibrium and the reaction composition, in theoretically. So for a single pure component, the Gibbs free energy depends on the temperature, pressure, and the amount of its components. So G equals G with respect to temperature, pressure, and the number of components, or the amount of the components. For a mixture, it depends on the number of moles of all species present in the reaction mixture. So G equals G with respect to temperature, pressure, N1, N2 to Ni, so the number of species, and also temperature and pressure. This only determines whether your reaction will take place. It doesn't tell you how long it will take. So you can only determine whether something's possible. Then you need to figure out how to make it possible within a specific amount of time. For example, glass is technically a liquid, but it takes hundreds of years for it to move. That's why you see all these churches with the glass slightly bent, because it's a fluid. So you can find that it's thermodynamically possible, but to make the glass move, to make it a fluid, you need to heat it up. That which determines rate. Using the rules of partial derivatives, the total differential may be written as delta dg equals the infinitesimal change in G over the change in P with respect at constant temperature and constant where the moles are the number of the species are constantly kept. So this tells you the effective pressure, the change in pressure plus the change in G over the change in T at constant pressure and then constant N, and dT plus, so this will tell you the effective temperature, dT with plus the sum of the infinitesimal change over of G over the infinitesimal change in Ni, so that's at equilibrium at constant temperature, pressure, and by changing the species. So Ni is changing, Nj constant. So this tells you the effective decomposition. The index Nj denotes that the mole number of all other species except I are kept constant. So if you change I, at any one point you're changing one species, one parameter, you can determine the others because it's a thermodynamic balance. So dG equals VdP minus SdT plus the sum of the infinitesimal change in G over infinitesimal change in Ni at constant temperature, pressure with changing Ni. So with respect to change in Ni. So if you change the species, the first species. For a reaction mixture at constant temperature and pressure, the first two terms drop out to leave the effect of composition. So because there is no change in temperature and pressure, you cancel out the first terms. So dG equals the sum of the change in G over the change in Ni at constant temperature and pressure with respect to change in Ni, the change in the composition of the first term. So the chemical potential mu I of any species in a mixture is defined as follows. So mu I equals change in G over change in Ni with respect to temperature, pressure, and changing species Ni. The chemical potential mu I of any species I shows how the total Gibbs free energy changes when making changes to the mole number of I, all while the rest are kept constant. Substituting, you get dG equals the sum of mu I dNi, and the Gibbs free energy depends on the number of moles of all species in the mixture. So that's something to take from here. Gibbs free energy depends on the number of moles of all species in the mixture. So that's what determines what minimizes the Gibbs free energy. That's why you reach equilibrium. So Gibbs free energy is just a way of describing a reaction equilibrium. A reaction thermodynamics. The equilibrium conditions must be sigma I mu I dNi equals 0. Hence, this means that it is necessary to find a set of Ni that minimizes the total Gibbs free energy, leading to dG at constant T and pressure to be 0. So this is how you determine the best thermodynamic route for a chemical reaction. It is necessary to remember that Ni cannot vary independently of each other. So you can't change the any one species without the rest changing. It's a stoichiometric balance. It just moves the equilibrium, so the rate is changed. Remember that the changes of Ni are related to the extent of a reaction through the expression developed earlier. So Ni equals Ni0 plus Vi epsilon. The differential form this may be written as is dNi equals Vi d epsilon. And substituting to the equation conditions gives the sum of mu I Vi d epsilon equals 0. So this minimizes your Gibbs free energy. As the epsilon must be non-zero, the above reduces to mu I Vi equals 0. So the change in the extent of a reaction cannot reach 0 if Gibbs free energy is minimized. Remember from the graph, you can only go so far before the reaction stops. This is the condition that a reaction system must satisfy at equilibrium condition. So at equilibrium, mu I Vi equals 0. The sum of mu I Vi equals 0. And what is needed is mu I as a function of Tp. Yeah, we know that already. So the total Gibbs free energy of a single component system is G equals G with respect to temperature, pressure, and N. In a closed system, Dn, the change equals 0, the change in the species equals 0, so, and the total differential of the G is dG, infinitesimal change in G over infinitesimal P T dP plus infinitesimal change in G over infinitesimal T with respect to at constant pressure with respect to change in temperature. And dG was obtained from the fundamental property relations dG equals BdP minus SdT. Therefore, it is possible to identify the first partial derivative, infinitesimal change in G over infinitesimal change in P at constant temperature equals V. Develop. In order to find the pressure dependence of G, integrate this from some reference pressure P0, so at any reference pressure, then between P and P0, so whatever your initial pressure is, with respect to change in pressure, is the integral between those two pressures BdP. Because sigma G over infinitesimal change G over infinitesimal P equals volume in a closed system. Simplified by using the integration by substitution rule, you can just integrate with respect to G, or rather change in G. So assuming the system can be described by an ideal gas equation of state, substituting for V is you know that V equals nRT over P with respect to change in pressure. So these show how the Gibbs free energy for a pure ideal gas changes along an isotherm. So between G and the initial G, to find the G, and the initial G equals nRT because only the pressure is changing, the volume is remaining constant with respect to dP over P. Therefore, G equals initial G plus nRT log of P over P0. The Gibbs free energy, like internal energy, enthalpy, and entropy, can only be found with respect to some fixed reference point. So you can only find it at a specific pressure, specific temperature, specific volume. It requires a reference Gibbs free energy to be fixed at the reference pressure before G can be found at any other pressure. So if you find it at specific pressure, then you can find it at any other pressure as well, based on the derivative. So chemical potential of a component in a mixture. Properties of ideal gas mixtures can be readily be found from Gibbs theorem, which states that the total thermodynamic property of any ideal gas mixture is the sum of the total properties of the pure species evaluated at the mixture temperature and the partial pressure of the species in the mixture. So mathematically, this can be expressed as M mix equals the sum of mk, k being the space. Where M mix is the ideal gas mixture property at temperature and pressure, at that specific temperature and pressure, and mk is the ideal gas pure component property at temperature and pressure K. So how each component behaves at that specific pressure and temperature. So you have the mixture with respect to the pure component. Applying Gibbs theorem to the Gibbs free energy, G mix equals the sum of GK over K. The ideal gas equation developed earlier for GK applies to any pure species K in the mixture. And for Gibbs theorem to apply, the pure species must be at a reaction temperature T and a species partial pressure Pk. Therefore, Gk equals the initial Gk plus NkRT log of Pk over P0. K refers to that specific pure component. So in terms of the Haber process, you're referring to just the nitrogen. So you can determine how how the components react together and also behave together based on the pure component properties. It's effectively like your when you're calculating density for a multi-component system, you take the density of each and balance them out. This is effectively the same thing. So note the special partial pressures, note the reaction temperature. Now substitute the latter into the former to get G mix equals the sum of G initial K plus NK RT log of Pk over P0. And the partial pressure is linked to the composition by Dalton's law. So Pk equals Pxk equals Pnk over the sum of NL, basically the species L. That's what I was referring to when I said it's a partial mix. It's effectively a mass balance of these. Substitute this last expression into the previous and you get G mix sigma K G0K plus NkRT log of Nk over sigma L and L P over P0. Therefore, G mix equals sigma K G0K plus sigma K NkRT log of N multiplied by Nk over the sum of NL multiplied by P over P0, and that extends to G mix the sum of Gk, the sum of the equation of state with respect to K, and the equation of and pressures, partial pressures, and with respect to the actual composition. Therefore, the definition of a chemical potential adjusted slightly to show that the total Gibbs free energy applies to a mixture was mu I sigma, not sigma, the infinitesimal G of mix over infinitesimal G of Ni at the specific temperature and pressure with I changing. If the chemical potential is needed, then the total Gibbs free energy of a mixture must be expressed in terms of mole numbers. So the number of moles, the change in moles. And this must then be partially differentiated with respect to Ni keeping temperature and pressure and Nj constant. So if you're referring to that specific species, so Ni, Nj, Ni being your first species, Nj your second species. Applying this procedure leads to the chemical potential Ui of the species I in the mixture. So mu I infinitesimal change in over infinitesimal change in Ni, basically doing a derivative. Actually, you don't need to. In the first summation, all the terms are constant except for species I, which is partially differentiated with respect to mole numbers of the species I, and all the other constant terms drop out, leading to the equation below. Look at it, go through it, It's useful for next year, but it's too much for this course. I'm just going to go over it a bit faster. The first terms on the right-hand side is simply the chemical potential mu I of species I with respect to pressure 0. So all you need to know from all this is if you're calculating Gibbs, the potential energy, the Gibbs free energy, and the chemical potential, you need to do it for every specific species. That's all. That's the main reasoning behind. Now you can calculate it using these equations. So each species would be, let's say, N2, H2 for the Haber process. So one is Ni and one is Nj. The first terms on the right-hand side can be written as infinitesimal change in G over infinitesimal change in Ni at a specific temperature and pressure and changing Ni. And have GI0, your initial GI, may also be expressed in terms of molar Gibbs free energy, so for specific moles rather than the whole system, which has the advantage that does not depend on the system size Ni, because it already takes into account effectively Ni, GI. So GI0 is GI 0 times Ni. Substituting this last expression into the previous one, you get infinitesimal change in GI Ni over infinitesimal Ni equals chemical potential. Hence, chemical potential is GI being the molar Gibbs free energy multiplied by infinitesimal change in Ni over infinitesimal change in Ni. Cancelling out, therefore GI equals the chemical potential at that initial stage. And the first term on the right hand side is the same as Gibbs free energy of a pure component I with respect to pressure. Substituting into the previous equation, turning to the second summation and looking at what must be held constant, all the terms within the summation drop out except species I. Also P and P0 are either constant or fixed. Therefore, chemical potential equals GI0 plus infinitesimal change in Ni over infinitesimal change in Ni, RT log of P over P0 with plus infinitesimal change of the summation over infinitesimal change of Ni with the species K. So the change in that specific species. That cancels out, splitting up the final term on the right hand side using the properties of logarithms. You get chemical potential equals GI plus RT log of P over P0 plus infinitesimal change over infinitesimal change in Ni, NK RT log of NK. And basically doing the second partial derivative, these two are the same. Hence, looking at the third term on the right hand side, all the terms within the summation symbol are constant except for species I. Also, temperature T must be held constant. So the temperature, remember, you only change one parameter at any time. Temperature is constant, pressure is constant, you're changing composition. And now apply the products rule to the third term. Therefore, mu I equals GI RT log of P over P0, infinitesimal change with respect to species I and with respect to NK. Cancel out, therefore mu I equals GI. And partially differentiating the last term of the right hand side to find the chemical potential of a component in an ideal gas mixture. If you look at the last term on the right hand side, all the terms within the summation symbol are constant, and except the species I, these are constant terms. These constant terms will drop out. Differentiating this, the final term leads to mu I GI plus RT log of P over P0 plus RT log of Ni plus that. That cancels out. That cancels out because they're constant. Therefore, mu I equals GI plus RT log of P over P0 plus RT log of Ni minus RT log of summation of NL. Using properties of logarithms, you get chemical potential equals GI0 plus RT log of P over P0 plus RT log of Ni summation of NL. And the terms inside the bracket are the mole fraction of species. The final results for the chemical potential of any species in an ideal gas mixture is mu I equals GI plus RT log of P over P0 plus RT log of XI. Notice the chemical potential is with respect to a fixed reference state, but is consistent with the reactor temperature and pressure and composition. So it's at that specific reference point. So at the specific temperature, specific pressure, and a specific chemical composition. Next step are to take the criterion for chemical equilibrium already developed, see below. Then you've seen this before. Then substituting the expression for ideal gas chemical potential into the above expression. After some manipulation, this will lead to the temperature, the criterion for equilibrium terms of temperature, pressure, and composition. Making the substitutions above, then the sum of VI, and if you put the chemical potential in, you get the above equation. Splitting up the summation terms, as well as taking constants out, the summation symbol leads to VI GI plus RT VI log of P over P0 plus RT VI log of Xi equals 0. And the overall stoichiometric coefficient has been defined as V equals the sum of VI. And the summation of VI GI 0 plus RT log of P over P0 to the power V plus RT log of Xi VI. So this is the same as the above equation. Rearranging, you get log of Xi to the power Vi equals log of P over P0 to power negative V minus Vi GI over RT. In mathematical terms, the sum of the logs is the same as the logarithm of the product. Mathematically, this expression below are equivalent to this. So the sum of log of Xi equals log of X1 plus X2. Applying the rule to the previous equation leads to log of pi I xi or to the power Vi equals log of P over P0 to the power negative V minus Vi GI0 over RT. Using the properties of logarithms, log of A plus B equals log of A plus log of E to the power B equals log of A E B. If you're not paying attention to anything, remember that logarithm rule, please, because that's quite useful to you in general. For the whole campaign, you guys actually suck at these normally. So remember logarithms. Pi I xi Vi equals P over P0 to the power negative V multiplied by E to the power negative Vi Gi over RT. Now, some of these thermodynamic terms will start looking similar to some previous ones you've seen. The reasoning is it's effectively balance of all. To simplify further, define the standard Gibbs free energy, change of reaction delta G0 at some standard pressure P0 and reaction temperature T. Therefore, the change in G0 initial equals the product plus the reactants. So you've seen that before, products plus reactants, products are positive, reactants are negative. So the VJ, GJ, the product, and the VK, GK. It's just the K and J just refer to that specific species. It's just a mathematical term. So delta G0 equals the sum of all the species VI, GI. Substituting this into the equilibrium relation leads to pi I xi to the power Vi equals P over P0 to the power negative V e to the power negative delta G over RT. And the units of delta G are J joules per mole, which makes it appear to be a molarity property. The units of delta G0 are joules per mole, but the denominator is per mole of a reaction. So it's not a molar property, it's per mole of a reaction. In other words, to convert the units of delta G0 from joules per mole to joules, you need to multiply delta G by epsilon. So remember, delta G0 equals Gi molar multiplied by epsilon, a factor that has a unit of mole. For 1 mole of a reaction, different amounts of each species are produced and consumed. This is why uppercase delta G0 is used instead of lowercase delta G0, differentiated from the molar properties, which are per mole of a species. So the equilibrium constant K is defined as K equals e to the power negative delta G0 over RT. Now, these are quite important things to remember. These are, the whole derivation is supposed to lead to these, by the way. And which leads to pi I xi to the power vi equals K P over P0 to the power negative V. And this is the general expression for a chemical equilibrium involving an ideal gas mixture. It relates the equilibrium composition to the equilibrium constant and the pressure of a mixture. So composition is equilibrium composition is related to equilibrium constant and pressure. All terms are dimensionless and includes pressure ratios. And in terms of some general reversible reactions shown below, A plus B plus C plus D. This leads to xc to the power C, xd to the power D over xa to the power A, xb to the power B equals K, P over P0 to the power negative V. Remember, the stoichiometric coefficients are exponents and they have signs. So the equilibrium constant is defined below. However, this is usually rearranged to show K equals e to the power negative G to the power RT, and delta G equals negative RT log of K. These are important parameter equations to remember. This expression allows Gibbs free energy of a reaction to be changed into an equilibrium constant and vice versa. And the Gibbs free energy of a reaction was shown to be given by delta G0 equals all the species VI, GI. Therefore, GI are the Gibbs free energy of a pure species at reaction temperature T and fixed reference pressure P0. Hence, each of the GI and therefore delta G0 and then ultimately K through its definition above depend only on temperature. And pure species GI are equal to the standard Gibbs free energy of formation of components delta G0 of formation plus the standard Gibbs free energy of its constituents. So in the tutorials and exam papers we'll go through more of this. This is more in line with the things you've studied in chemistry in either advanced hires or hires as well, and A levels, I assume. The Gibbs free energy of formation of an element is taken to be 0, so GI 0 equals delta G F, the delta G of formation I. Therefore, the standard Gibbs free energy of formation delta G F formation I are known for all component species at 298.15. So that's pure component parameter, going back to when you calculate G with respect to a specific pure component. Thus, hence, delta G0 may be found at 298.15 K from delta G at 298 is the sum of VI delta G of formation I. A formation reaction is written in terms of 1 mole of a compound, so these are from your steam tables, even though they're not steam tables. Formed from its constituent elements at 298.15 K. Gibbs free energy of a formation has a units joule per mole, and delta G formation is per mole of a compound formed. and it is a molar property since it's per mole of a particular species. If a value can be found for a standard Gibbs free energy change of a reaction delta G, usually at 298.15 K, then substituting delta G equals negative RT log of K, hence the equilibrium constant K may be found usually at 298 K, and equilibrium relation may be solved. Therefore, pi I xi to the power Vi equals K multiplied by P over P0 to the power negative V. And notice that the individual composition xi are not independent. To solve this equation, all the xi are replaced by a function of epsilon. So this, to find, it has to be in terms of epsilon, because you have xi, xj, and xk, and it needs to be in terms of where the reaction is. Once a single value for epsilon has been found, then all the xi may be recovered for each species.